Let's look at our last topic in section 3.5, and that is on graphing rational functions. Much like we did with graphing quadratic functions, and especially graphing polynomial functions, we're going to take a number of the individual topics that we've already looked at in the chapter and put all those items together in a step-by-step procedure to graph the function. Let's review that graphing procedure in the Graphing Rational Functions handout. We'll use this 6-step procedure for graphing rational functions. You'll also see this procedure in the textbook. Our first step will determine symmetry. Very often this step isn't very helpful, but especially if you get even or y-axis symmetry, that can be useful. And next, we'll find our intercepts. We could find the y-intercept just as we did with quadratic and polynomial functions by substituting x equals 0 into the function. And we'll also find the x-intercepts. We'll set the numerator expression, p of x equal to 0. And we can also look at the multiplicity of those intercepts like we did with polynomial functions. Then we'll find our asymptotes. Remember, we'll set the denominator, function q of x equal to 0 to find vertical asymptotes. And then we'll use this methodology to find our horizontal asymptotes. And then we'll use all that information from steps 1 through 5 in the asymptotes to frame the picture and get started. Then, in step 6, we're going to pick points strategically to fill in the graph. So we don't necessarily want to pick random points. We want to pick points in an intelligent way to fill in key missing pieces of the graph. And we generally like to choose integer values to substitute into the function because they're easier to evaluate. And generally, we'd like at least 3 points for each section of the graph. I will try to illustrate this as we go through the examples. In step 1, we're going to try to evaluate the symmetry of the function. And so we evaluate f of x at minus x. So we'll substitute minus x for x and evaluate, and we'll get this expression minus 2x minus 1 over minus x minus 1. Now clearly this isn't what we started with, so it's not even. And remember, if it were odd, it'd be as if a negative was distributed across the entire function. So that would look like minus 2x plus 1 minus x plus 1. And that's not what we have here either. So in this case, and this happens quite often, the symmetry is neither. In step 2, we find the y-intercept. Just as we did with our other functions, we just substitute x equals 0 into the equation. And when we do that, we'll get minus 1 divided by minus 1, which is plus 1. And again, I'll write that as 0, 1 in coordinate point form. In step 3, we find the x-intercepts. So we set the numerator expression p of x equal to 0. Setting 2x minus 1 equal to 0, we'll find that x equals 1/2. But we'll also utilize our multiplicity concept from graphing polynomials. This factor really has a multiplicity of 1, which is odd. So the graph will cross the x-axis at the coordinate point 1/2, 0. In step 4, we find the vertical asymptotes. So now we set the denominator expression q of x equal to 0. Solving that, we get a vertical asymptote at the line x equals 1. In step 5, we find the horizontal asymptote. And looking at our function, we see the degree of the numerator and denominator are both the same as a value of 1. That's our case 2. So the ratio of the leading coefficients would be 2 over 1. So our line for the horizontal asymptote is y equals 2. Now that we've gone through the first 5 steps of the graphing procedure, we want to use all the information that you see here in red to start to frame in the picture before we do the final graphing. And in particular, you want to first draw your asymptotes and put in your intercepts. And then we can figure out which points we need to select to fill in the graph. I've now plotted our asymptotes. Here's our vertical asymptote at x equals 1, and our horizontal asymptote at y equals 2. And here's our y-intercept and x-intercept. Now our graphing procedure in step 6 says plot at least a point beyond and between each x-intercept and its asymptote. So if you look carefully at the picture, it seems like we have a part of the picture here, and then another part of the graph might be over here. So I want to pick a point in between this x-intercept and the vertical asymptote, and another point here at x equals minus 2 to confirm this part of the graph. And then I'm going to point pick points x2, 3, and 4 to see what's going on in this part of the graph. Substituting the values of x equals -1 and 3/4, we get these two coordinate points to help confirm what's going on in this part of the graph. So when we fill in those 2 points, -1 will be here at 3/2, and this fractional value, unfortunately I had to pick 3/4, but it gives us this value of -2. So now it really seems to confirm the shape of the graph in this part of the coordinate grid. Now let's pick some points to confirm what the graph looks like over here. Substituting the values of 2, 3, and 4 into our rational function, we get these coordinate points, and now we can complete the graph. So we'll have when x is 2, y is 3, then we have 3 or 2, 5/2 or 3 and 2.5, which would be about here, and then 4 and 7/3, or 4 and about 2 1/3. And so we see there is that other section of the graph, and we have at least 3 points for each section. Again, with step 6, use all the other information to frame the picture from steps 1 through 5. Fill in your intercepts, and then pick a few key points strategically to fill in the graph. Let's look at example 6 on page 420 of your textbook. So, now they've given us f of x equals 3x squared divided by x squared minus 4. So again, step 1, let's look at the symmetry. We'll substitute minus x for x into our function. And because of these even exponents, notice when we evaluate 3x squared over x squared minus 4, that's the same as what the original function is. So now we know we have even or y-axis symmetry. Even symmetry is always helpful in any graphing problem. You know at the end that you should have a mirror reflection around the y-axis. So that will be helpful in this problem. Step 2 is find the y-intercept. So we'll substitute 0 for where we see x into the function. We'll get 0 divided by minus 4, which is 0. So in coordinate point form, that will be 0, 0, or the origin. In step 3, we find the x-intercept. So we set our numerator expression equal to 0. So we'll set 3x squared equal to 0. And of course, that root is 0. But remember, we can use our concept of multiplicity here. The real factor here is x squared. That multiplicity is 2 or an even number. So we know the graph touches and turns at that point 0, 0. In step 4, we find the vertical asymptotes. Again, we'll set our denominator expression q of x equal to 0. Setting x squared minus 4 equal to 0. Of course, you could factor this to x plus 2, x minus 2, but those will be your solutions in vertical asymptotes. We'll have 2, one at positive 2 and one at minus 2. In step 5, we'll find the horizontal asymptote. And when we look at our function, right, the degree of the numerator and the denominator are both 2. They're the same. That's case 2. So again, the equation for our horizontal asymptote will be the ratio of the 2 leading coefficients here, 3 and 1. So y equals 3. Now that we've gone through the first 5 steps, again, let's use all the information we have identified here in red to start to frame the picture. So I'm going to draw in the asymptotes and the intercepts initially. Now I've plotted our horizontal asymptote here at y equals 3 and our 2 vertical asymptotes at x equals plus or minus 2. And both of our intercepts are actually in the same spot. So when we want to look at, well, what other points are we going to choose to fill in the graph? You can see there's almost 3 sections to the graph. One sort of generically here, one in the middle. Clearly there's a point here that must be part of the graph here. And then another third piece. So again, let's pick some intelligent points. For instance, in the middle, let me pick positive and negative 1 for x to fill in this part here. When we substitute x as minus 1 into the function, ultimately we get a y value of minus 1. And notice, when we substitute x as 1 into the function, we also get minus 1. So when I graph those points, they'll both be here. And remember, too, we know the graph touches and turns at this x-intercept due to the multiplicity. So this graph will really look something like this in this part. And if you look at the points that we calculated, this really is our definition of an even function, right? F of minus x, this y value, is the same as f of x, this y value, and we see the symmetry. And so this is where if you get even symmetry, it can really help you with your graphing. Let's pick just a few more points to fill in and complete the graph. Now, I'm going to show you the calculations for x's minus 4, minus 3, and 3 and 4. But remember, due to the y-axis or even symmetry, you really only need to do one set of these. For instance, if I evaluate f of 3, and that's 27/5, or that's 5 2/5 in mixed number format, and f of 4 is 4, I'll get that coordinate point of 4 and 4. Notice you'll get the same y values for the negatives on the other side due to that symmetry. So when we plot these points, 4, 4 will be here, and this will be about 5 2/5. And again, we're going to have the same symmetry on the other side. And so that part of the graph will look like that, and this part of the graph will look like that. And of course, we have that visual symmetry around the y-axis. So again, remember, in step 6, before you start picking points, be strategic about it. Fill in as much information as you can from the first 5 steps and try to pick points that will fill in the graph and confirm its shape in all parts. Now do pencil problems 6a and 6b, where you'll graph a couple rational functions. And definitely follow the 6-step procedure outlined here and work the problem on paper so you get practice creating these graphs manually, step by step.